Okay, coming back to this part of the lesson. So we will resume our lecture today by discussing about how to use relay logic using logic ladder. Uh, so basically, the when we want to create a logic ladder, we need to use the two vertical lines basically. Okay, on the left and on the right. Okay, so before that, let me keep. We need we need to see the input and output components. Okay, to help us to decide or to come out with the logic ladder. So we need two vertical lines basically. Mhm. Okay, on the left we have the high. Okay, line or basically the input. Okay, we represent that high, and then the on the left, on the right basically is the low lines or uh, the the ground part. Okay, so our uh, logic ladder, we going to draw or produce it in between these two lines. Okay, so that's between these two lines where our logic ladder will go. Okay, so and then there will be some part, okay, of the logic ladder called rungs. Okay, we will, okay, rungs, which will represent the ledger logic uh, logic ladder. Okay, so the our task is to control, okay, basically the extension and retraction of a air cylinder. Okay, so this is a air cylinder. Okay, whereas the extension, okay, the extension of the uh, arm, okay, basically controlled by uh, two motor which run the compressor. Okay, so there are two motors, okay, run the which run the or basically which will uh, take turn to turn on the compressor, whether to pump in pressure or take out the pressure, okay, from the compressor. And okay, in the last lesson we have look at a few position. Okay, the first position is the uh, default or original position. Okay, and then second, where the uh, extend when the extend motor is energized or turned on, and also the start button was pressed. So we have the main movement on the second process. Okay, the drill will go down, okay, in between, basically between point LS1 to LS2. Okay, and the third is when the arm or the table that hold the drill is also connected to the extending or the main arm, okay, where it arrive at LS2. So so the origin is when the basically the drill, okay, or the table is level at LS1, okay, LS1, and it's where we wait for the start button to be pressed, okay, to be pressed, and then when the start button is pressed, so we can set a control relay to be high, okay. So let's start by drawing the, okay, start button. Okay, start button. Let's say there is a terminal, okay, where we have a start, okay, button, and then a stop button. Okay, the start button, okay, is normally open momentarily push button. Okay, then in series with a stop button, which is normally close, okay, normally close push button, and set high, okay, to a control relay. We name it as CR1. Okay, this is uh, we call it as the start sequence. Okay, but the thing is about this start sequence, uh, the push or the start button is a momentarily normally open uh, switch, which means that uh, when there is no uh, pushing force on the button, it will always off. But when when a user, okay, press the start button, okay, so it will complete the circuit, okay, the first rung, and CR1 will be energized, okay. But immediately when we remove or the pushing force on the start button, so CR1 will be de-energized, okay. So we need to have a capability so that the start button, when we press it once, so CR1 will uh, remain on, okay, remain on until we send a uh, stop signal. Especially in this case, we set stop as a, okay, emergency uh, mechanism. When we press stop, so it will break or stop the current from flowing from the left line to the right. Okay, or other words, CR1 will be immediately uh, de-energize or turn off. So we to have a what is called as a self-holding circuit. So we put the contact of contact relay CR1 in parallel with the start button. So CR1. So this is called as the self-holding circuit. Okay. So when we uh, give a or push the start button, okay, so the above top part of the circuit will be complete and allow the current to pass from high to low. So CR1 will be energized. In the same time, okay, CR1 contact will high or okay high, and then it will hold. Okay, this it will hold the control relay one to be self-sustaining, okay, or self-holding. Okay, we will uh, remain on until we press the stop button, which will immediately uh, cut off the start sequence. Okay, so CR1, okay, we use that as a start sequence. Okay, and this is the first part. Okay, so the second part, okay, you see we have CR1 contact, which uh, send the signal to the system to start, and also we have to check the condition of our input uh, components or input transducer. So in this case, we have limit switch 1 and limit switch 2. So limit switch 1, we set it as normally open. Okay? And LS2, we set it as normally closed. So to okay to okay after we start the sequence, so have a start sequence, so we want to proceed with the next stage. So we uh, okay connect the CR1 contact, okay, with the limit switch, okay, LS1. So LS1 is normally open, normally open. So and next we have a LS2. We set that as normally closed. And we use the start sequence and then the inputs from LS1 and LS2 as the second rung as a condition. Okay, C, R, 2. So this is okay. Basically, this one is like input condition. Okay. Okay, so this is the input condition. Okay, so after the start sequence, you will check the condition of LS1, okay, LS2. So when okay, LS1, oh sorry, when CR1 is energized, so contact relay become high. And when the table is at the first position, so LS1 will be closed. So LS2, okay, is set as normally closed. Next, it will, okay, de-energize CR2. Okay. Then we need to have a output, output rung. So the output rung, okay, CR2. Sorry, CR. So okay, so CR3 now becomes the output, okay, main output to energize or de-energize the extension solenoid or motor. Okay, so and then also, of course, we make it as a self-holding, and the output contact of CR3, okay, we use it to basically to control the condition of three output device. The first is the extend, and the second one is the retract, and also the drill motor. Okay. 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 So when the first condition is fulfilled, CR2 will high. Okay, CR2 will high, and then check, and then CRT will be the output self-holding. Thus, automatically will turn on the extend solenoid, which will, okay, send the pressure to the compressor, so extend, okay, the arm, and then at the same time, okay, the drill will turn on. Okay, so that, okay, happen for at the second part, when after start button is pressed. Okay, and then when LS2 is input, or the table is hit the limit switch 2, so here will immediately the change the condition of the LS2 switch on the logic ladder. Okay, for example, it will like break this output, and also will break the input. So in turn, it will de-energize CR2 and CR3. Okay, de-energize CR2 and CR3. So the extend, okay, will extend coil will be off, and also the motor will off, and then de-energize the retract. Okay, and then the cycle will continue. Okay, will continue. Okay, back to the check in the second condition, okay, until the stop button is pressed, okay, in any condition lah. Okay, so after the first sequence, okay, so the cycle, okay, will go from 2 to 3 and then back to 2, and then 2 to 3 back to 2, and then 2 to 3 until stop button is pressed. Okay, when stop button is pressed, it will go back to the original, okay, sequence. So this is a method in drawing the logic ladder line by line, considering the sequence or the condition of the process. Okay, there are methodological method like melee machine, melee or more. Okay, it's called as finite finite state machine, FSM. So where you consider the number of input and then the output condition, you draw the logic condition, and then can come out with the logic sequence. But we are not going to cover that in details. So just show you how to create logic ladder based on the conditions. Then we have other input in here, input device as a can be used as a logic controller or sequence. In this case, we have a flip-flop. Okay, flip-flop is a device, edge, basically an edge trigger device, where the we have a set of input of the flip-flop. Okay, input input or the condition which the output okay, is triggered by edge, input edge. Okay, then the condition of the output, okay, will determined by the condition of the input. For example, here we have a SR flip-flop. Okay, whereas when the input SR is set low, okay, so the condition of the output will not change. Okay, and then if the input is set at 0, 1, so the output, okay, the next stage of the output, when it receives an high on the trigger, high edge on the trigger, it will change from or it will reset the output to 0. And when SR is 1, 0, so it will set the output. Q bar is the negative or negate of the output, okay, the main output. But for SR, when set 1, 1, so the output will not be valid or random. Okay. Then as an improvement, we have a JK flip-flop. JK flip-flop, the first three conditions same as the SR, except that when we set the JK input high, both high, so every time the JK flip-flop receive a in the clock trigger receive a high, okay, in this case high input, the high input, so the output state will be toggle. Okay, toggle means that, okay, let's say uh, uh, Q11, okay, let's say the first trigger output is 111, but the next trigger, okay, so the output, okay, the next trigger, okay, we will basically toggle our 0, and then next 1, 0, and so on. So that's a flip-flop, okay? And this example, using flip-flop to control an industrial surface grinder. So this example application is using the edge trigger JK flip-flop as in a circuit to control the operation of the surface grinder as shown in the figure. Okay. So the circuit is simple. The connection of the circuit is simple, where the input of the JK flip-flop, okay, is set high, and then the clock, okay, the clock input, okay, okay, the signal is controlled by two limit switch, LSH and RSH, or which are connected in parallel. Okay, so every time the limit switch is either the LHS or RHS is close or turn on, so it will send an input signal to the JK flip-flop, okay, thus change the uh, position or change the condition of the output, okay, the output. So the actual setting, okay, looks like in the figure here on the top and also in the bottom. Okay, so whereas the system basically, okay, operate, okay, the purpose is to polish an item which is placed in between a grinding wheel and the table. Okay, so basically what is intended here is to the table, okay, to move uh, back and forth, okay, left, right, left, right, okay, which the motion left and right is controlled by a motor, okay, by a motor, and then the motor, okay, is basically uh, wired or connected to change, okay, its uh, the turning direction, okay, based on the output of the JK flip-flop, okay, or the Q output. So the Q output will will determine whether the forward motor starter is turned on and vice versa. Okay. So it works like in initial, let, let's say when the system start, okay, let's say the motor is turned on, and then so JK in this condition, when you set JK high, so the output, okay, will be either Q1 high or Q1 high or low. So let's say when the system start, Q, okay, equals to 1, okay, which, okay, turn on the forward motor, okay, motor starter, turn on the motor starter, thus, okay, turning the table, okay, from let's say left uh, to right, okay, okay where the motor will turn on the screw, okay, this is the screw which connect to the bearing, and the bearing will, okay, let's say will make the table to move from left to right. Okay, let's say start from the middle. Okay, we start table at the middle. Okay, and then Q. Let's say Q1 is high. Start from left to right, and in this part, okay, C. Uh, okay, no edge, no edge. Okay, so the table will move to left to right. Okay, so when let's say RSH is contact, or there's a contact or close, okay, so C will receive a high, okay, high H trigger, okay, basically, okay, and we know that JK is set high, so Q, okay, from 0 now change to 1, as to from 1, Q from 1, the state before, okay, because it now it receives the high H input, so Q now turns to 0. Okay, so Q 0, so FMS off. Okay, and this one is FMS on, and Q bar will be 1, and then the reverse motor starter will on. Okay, so here what happened in the second stage, okay, the table here will, okay, move right to left. Okay, so it will table will move from right to left, okay, until uh, okay, until the left hand side switch contact close. Okay, so it C now will send, okay, an edge the pulse. Okay, okay, so that Q now become 1, so FMS on, okay, and RMS off. So here the table will move from uh, left to right. Okay, so it will cycle, okay, will go on back forth from left to right, okay, until uh, the main power is turned off. Okay, until the main power, so the system will continue. So this is an open loop, as we don't check the condition of the uh, workpiece, or we just use the human operator to check whether the process has completed, so that the system can be turned off. So this is one we have using a flip-flop to control an industrial surface grinder. Okay, so next, where we have discussed a bit how a flip-flop can be used to a signal output can be sent to a motor direction control, okay, circuit. So in this part, uh, we will look into basically uh, a polar reversal technique, polar reversal technique, or basically to reverse the direction or the rotation of a motor, okay, technique, okay, by using a relay. So in this case, we have a double pole, double throw relay, okay, double pole relay, okay, to control the current direction that flow through a motor winding. So here we have our output, okay, a motor winding, okay. On the left, so here we have our control circuit, and here we have our power supply of our output. Okay, so in this case, we use the relay, okay, to separate the control input and then the output, okay, the output circuit, so that uh, the level, okay, here in for the control circuit, we set at 5 volt low voltage, and then the output, okay, can be set at higher voltage. In this case, we set at 12 volt. Okay, so we know that the rotation or, okay, direction of a motor depend on the direction of a direction of the current that flow through the motor. Okay, if we change the direction of the current, okay, it will change the induced magnetic field that will basically interact with the stator or the permanent magnet, and eventually can change the direction of the rotation. Okay, so we have we have here a few important things that we need to cover here. First, we look at the uh, control signal here. Control signal. So our control signal, the main power supply is 5 volt. Okay, and the main control signals, okay, it may come from an electronic circuit or microcontroller, which send the signal, okay, okay, to the gate, okay, of the N channel MOSFET. Okay, so this is an N channel MOSFET, whereas the source is connected to the ground. Okay, so when the control signal is high, okay, or JS is set above the threshold, it will basically allow current to flow from the drain uh, to the source. Okay, and when that happens, when the control signal is high, it will energize the relay solenoid, and then you will create the electromagnetic pulling force and change the contact position of the relay here. Okay, okay, and there's another important component here. Okay, this is uh, basically a simple diode. Okay, the thing is that for solenoid is an inductor device. It behave like inductor. Okay, so when we energize okay the solenoid, okay, so we give current to the solenoid, okay, it will energize, okay, the solenoid and then generate electromagnetic field. But the thing is that when we remove the current that flow through the coil, okay, so it will generate a back EMF. Okay, back EMF. Okay, back EMF. Okay, when let's say I here, the problem is when we set at 0 after we energize. Okay, okay, set at 0 uh, from uh, from high is let's say high, and then we emit, and then we suddenly, okay, remove the current, or suddenly the control signal is low, so current I will become 0. So thus will, okay, here will be generate back EMF. Okay, so to avoid the generation of the back EMF, we set, okay, here diode. Okay, basically we give a diode here. This diode is D1F5819. So when the load is de-energized, so the diode become forward bias. The stored energy is dissipated back through the coil, and then the voltage driver is clamped to 0.7. So instead of V here, okay, V here become negative LDI/dt, so V is limited to, okay, 0.7. So it's when I is 0, so V is stay at 0.7. So no back EMF. So 0.7 is not large enough to generate a electromagnetic field through the solenoid. Okay. So if we don't put this, it will basically create a false uh, signal, and then will force the relay, okay, to change, okay, or to generate a false pulling force at the opposite direction. So it will basically create a false uh, sequence, and then it followed by a very an audible clicking noise. Yes. So that's the purpose of the uh, diode. So this diode is called as the freewheeling diode. Okay,
Please,
yeah,
please, Prof, this diode, Zener diode or normal diode?
it's a Zener diode.
Okay, then it's not supposed to be its value, for example, 0.7. volt. I think because if we take a look at the power supply, for example, 5 volt there. So I think the inductor will not make a magnetic field just by point 7 volt. So
Yeah,
what we have to do with this diode?
so you're correct. So it's not supposed to be a Zener diode. Zener diode has a larger back EMF. So you can use it's basically let's check the sorry the component 1715. Yeah, it's a Schottky diode. It's not a Zener diode. And then there's forward bias is 0.7. Okay, the forward bias is 0.7. So we connect it that way. Okay, this way. When back EMF is negative, so it will forward bias the diode and then limit the voltage at 0.7. Okay, so the voltage across the solenoid will never go through 0.7. But when current when the solenoid is energized, it's no problem. So this diode will not be functioning. It will only functioning when we remove I, okay, suddenly to zero. We cut it off suddenly. So because solenoid is an inductive component, so it has the characteristic to oppose any current change. Okay, so when we try to cut it to zero, so it will oppose that current change. It will try to induce, okay, give it or don't go to zero current. I give you back, try to induce more current. So that's why it induce a back EMF. And then the opposite current, the current that it induces or by the solenoid is the other direction. So when we remove I suddenly to zero, okay, so the solenoid, okay, here the solenoid coil, okay, will induce back EMF. So back EMF, and then it, okay, that EMF, if we don't put this diode, so the voltage here will be negative at high, very high is the sudden, okay, oh, sorry.
Prof, please.
Yes.
Thank you. 5 V1 is 5 volt, yes, and it is DC voltage.
Yeah, DC voltage, true.
Okay, okay. Then
DC.
in this case, I don't know. I couldn't understand exactly
Okay.
what the mean of this circuit. But in my just to
Okay.
say what I
Listen.
understand,
Yes.
because this is DC motor, I think
Mhm.
we don't have to use Zener diode or any diode here because always 5 volt. So the inductor will bring will make the magnetic field to bring to change the director of motor. So
Okay.
what? So for example, if 5 volt was or were AC, we of
Mm.
course we need to use diode. But here, what's the mean of this diode in this circuit?
Okay. That's actually a good question. It's not about the motor. Okay, it's not about the motor, but it's about the control circuit itself. Control circuit itself. Okay, so uh, so this is I is the control uh, current. Okay, that flow through the solenoid, right? Isn't it? And then it is also connected to the control circuit. Okay, so this control circuit may come from let's say microcontroller. Okay, microcontroller. I'm telling you this because this is my real experience. Okay, using I'm using the same solution lah. Okay, to turn on my application was just to turn on the motor, not to change the direction, just turn on. What happened? Okay, when I turn on, okay, and then turn off the signal, so it sends a false uh, uh, current back to the main control circuit, to the microcontroller, because it is interconnected through the MOSFET. Okay, basically send and then reset my microcontroller. Okay, now the thing is like this. uh let's say I, okay, the level of the current 0, we draw is as a versus the time lah. Okay. So when, okay, and then the bottom here we have our GS. Okay, or let's say this is from our V in lah. Okay, the input. Okay, okay, so when we, okay, V in time. Okay, so we when send high, okay, high here, high in this, so we'll allow the current to flow from D to S. Okay, okay, that's is that clear? Okay, okay, when this is high, so current here, okay, okay, will flow. Okay, that's fine. Okay, that is fine. Okay, and let's say V is the voltage across the solenoid. Okay, V is the voltage across the solenoid. Okay, that is fine. So when we give high input to the V in here, okay, high. Okay, let's say this is 5 volt, right? So this is current flow. So this is when V1, okay, is 5 volt. Okay, that's fine. And this let's say the voltage across here, okay, solenoid is relatively low lah. It's low. Okay, low because this is solenoid. Okay, this is a low resistant solenoid. Let's say the level is low. Okay, never mind. Okay, you put. Okay, so it does. So we look at so the whole circuit. Okay, V is in parallel, in series with DS, and also GS has some electronic connection lah to the V in. Okay, so when we remove I, okay, suddenly to 0. Okay, what we expect that, okay, V will go back to 0. That's what we expect. Okay, but because this is an inductive load or inductive device, so what happened? It will generate a back EMF. So V is, there's a back EMF. There will be a spike, negative spike, and that happened very fast. That negative spike, okay, will send back here, and then you will, okay, basically interrupt your, in my case, interrupt my electronic microcontroller. So microcontroller become reset. So that's my real experience. That's why we need this, okay, to, okay, remove this.
Yes, yes. Now it's very clear. Thank you so much.
Okay,
Yes, yes,
so
yes,
it's not about the motor itself. Okay,
yes.
but the control input and then also the relay.
Yes,
So
but it
that,
is so complicated when you think, for example, about what we have to do with this diode. If we don't have a real experience, as you
yeah,
mentioned now, you will not able to know what is the main reason to use this diode here in this location. But now it's very clear. Thank you so much, Professor.
yeah. When this will happen when you want to drive a motor, okay, using a microcontroller, it will happen. So this back EMF phenomenon. Yeah. So your question is good, because I thought that you have the same experience or idea. So so the main idea of the here is the Schottky diode is to protect, okay, the control circuit, okay, and also the relay. Okay, otherwise it will create a very large back EMF, and it can be heard from the clicking noise. It's audible. I mean, eventually will two things will happen. First, we reset your microcontroller, and also will somehow, or if unfortunate, will break down the basically the relay. Okay, right. Okay, so that's the purpose of the freewheeling diode lah, to protect the input control the circuit. Okay, so the function here, so when we give signals to the uh, N channel MOSFET, it will control, or basically control the current of I here, and then we'll change the contact of our double pole double throw motor. So basically, when I uh, we don't start with I. So this one we rename one prime, two prime, two prime, three prime. So where V in, let's say V in is low. Okay, so low. So basically I is 0. Okay. So the contact, the relay at this condition when I is 0. Okay, the contact is 1. Contact with 3. Okay, and also 1 prime contact with 3 prime. Okay, so the current of V2 relay, let's say this is point A and point B, and then let's say we I2. So at when V in low, current flow to the relay will be 0, and then the contact, relay contact, okay, the first set is connect to 1 3, second set is connect to 1 prime to 3 prime. So the current flow, okay, through the motor winding is from A to B. Okay, so when B is high, okay, current will be more than 0 lah, or high. So we will change the contact position. Okay, so the relay from 1 to 3 change 1 contact to 2 and 1 to 2 prime. Okay, and change the direction of the current I2, okay, from A to B to B to A. Okay, B to A. And okay, manipulate, say the direction. So let's say this is clockwise, and then this become anti-clockwise. Okay, so this is one way of polar reversal technique, okay, using a relay. Okay, and there are other inputs or controller devices, to control sequence of your system, like for example a counter, okay, and shift register. I don't want to discuss that in details. So this is an example of asynchronous 4-bit counter, and where it counts, okay, from 000 until 111, okay, but in sequence when it receive a clock. And then we have a shift register, okay. Just give you some idea the one not going to ask, especially in the test or in the final, just will give you idea of some other controller devices. Okay, then we have input devices. In this case, sensors and transducer, which are used as input devices. Let's say in what we have here, okay, optical sensor, uh, proximity sensor, and pressure sensors. So these are type of input devices used in logic or industrial electronics. Uh, so we look into some of the input, the principle of the input devices. Uh, we have inductive sensors, based input devices based on resistive sensors, and then we also have inductive and capacitive, and also piezo and radiation sensor. We will look into some in details. Okay. For instance, here we have a resistive, okay, resistive sensor, which is based on the resistive change. Okay, the input parameter change in proportional with the change of resistance of our sensor. Okay, and this is what it seems a typical displacement sensor based on potentiometric displacement sensor. Okay, so it can see the displacement sensor here. Okay, involve the action of a displacement in moving the wiper of the potentiometer. So this displacement basically, okay, happen at this part. Okay, okay, where this part is attached to an object that move or displace. Okay, then we want to, okay, measure the displacement. Okay, basically this device convert the linear displacement into a changing resistance of the device that may be converted directly to voltage. Okay, so from displacement, okay, so it basically change the resistance, okay, of the device, and then we can use the change of the resistance to get the output. Uh, so we use the output, okay, as a signal to our as a application. So it basically rely on the change of resistance. So you can see here, there's a wire wound in the middle, okay, in between point 1 and 2. So that represent the basically terminal 1.2, okay, represent the total resistance of the device, okay. And then there's a wiper, okay, that move, okay, from point 1 and 2. So it will change, okay, basically the resistance between 1 and 3 and 3 and 2. Okay, so basically R, the resistance between point 2 and 3 and resistance point 1 and 3 will be in portion to the displacement. Okay, displacement. So this is an example where we will look into how we can use this device to measure displacement, but we will look into a few cases lah. Look how we can practically use this device. But before we proceed, let's have a 7 minute recess or break. Okay. Okay, let's come back to this example. So we have a potentiometric displacement sensor. Okay, here. Okay, uh, let's say R the fixed the R sensor we have here. R sensor represent the resistance change of the potentiometer. Okay. Um, so let's say R sensor, we say R point. So we have okay, I redraw 1, 2, and 3. Okay. So let's say we use R3 to representing the output or proportion to the displacement. Okay, displacement or that we want to measure. Okay. Uh, so we want to measure the displacement 0 to 10 centimeter. Okay, 0 to 10 centimeter. And the total resistance, okay, 1, 2 is basically 1 kilo ohm. Or we want that change. Okay, 0 represent 0 volt. Okay, or 0, 0 represent 0 volt. Okay, and R12, and then 10 centimeter. Okay, represent 10 volt. So we try to have okay the output okay to be up like that. Okay, so maybe the simplest way is to use to connect the sensor into a divider circuit. Okay, so maybe what we can think like just connect. Okay, the input is 10 volt. Okay, 10 volt. Okay, so and then we take this as V out. Equivalent to R32 over R13 plus R32 multiply with the input, which is 10 volt. Okay, so what we expect using this arrangement, so we want like ideal the output. Okay, let's say this is the displacement X, delta X, and then the V out, okay, 10 volt, 10 centimeter, and then the output 10 volt. So what we expect that the output, okay, will be linear according to this equation. Okay, that what we expect. But in reality, the output, okay, is not ideally ideally proportional. it will have some non-linearity. Okay, so it will be some non-linearity, or it may behave differently. Okay, it may not be proportional. You see here, they uh, basically the displacement, okay, okay, basically change the resistance between 3 and 2 and 1 to 3. So the function of R32 for this instant, okay, is on the uh, numerator and on the denominator, okay, R32. So we need something like uh, need something like the output of the sensor divided by a fixed resistor, like R32 divide by a fixed resistor lah. For example, fix. Okay, so if we have the change of the sensor divided by a fixed resistor, uh, multiply with the voltage input, so we can have a somewhat good linearity. Okay, so one way we can do is by using so uh, so we can create uh, okay, we can create an inverting amplifier. Okay, so the V out here, so V out can be, okay, something like V uh, R32 over a fixed, okay, fixed RA, we can put a RA here, multiply with our V in. Okay, V in, okay, somewhere here. So we need to create an inverting amplifier, so that the output, okay, R32 will be divided by a fixed uh, resistor, multiply with the input voltage. Okay, so it can be done, okay, by choosing several. So our so we expect that the output V out, okay, to be equivalent R32 over RA, a fixed resistor, okay, negative inverting, multiply with the V in. Okay, this is a inverting amplifier. Okay. so it, so the whole circuit can be done like this. Okay, using negative 15 volt power supply. Okay. create a biasing Zener diode. Okay. So this is our RA. This is our R. Itu our sensor. Okay, this is our V out. Okay, so we going to use a Zener diode to so that V in here. Okay, we bias the Zener diode, and this is a fixed resistor to bias the Zener diode. We just choose 250 ohm. That's fine. Okay, so we can choose Zener diode. Okay, let's say 5 VZAX, the reverse 5.1 volt. Okay, 5.1 volt. So when we bias, okay, this is the biasing of the Zener diode. So we will produce a constant V input equivalent to negative 5.1 volt. Okay, so then we need to choose uh, the proper value of our RA. Okay, so we expect that our output, okay, V out, okay, to have a maximum 10 volt. Okay, when basically when the displacement is at 10 centimeter, 10 centimeter. Okay, so, and when at 10 centimeter, the equivalent value of RS30 R32 is equivalent to 1 kilo ohm. So when delta X is equivalent to 10 cm, okay, V out is 10 volt, and R32 is 1 kilo ohm. Okay, according to this specification here. Okay, so we can use this formula. So when V out 10 volt equivalent to negative R32 is 1K divided by RA multiply our V in is fixed, negative, okay, 5.1 volt. So we get that our RA is equivalent to 510 ohm. Okay, so in this case RA is equivalent to 510 ohm to drive the circuit so that we can measure the output or have the output proportional from is proportional to the displacement. Okay, when the output or the displacement is zero, the output is zero, and will linearly increase. Okay, uh, to 10 volt maximum when the displacement is at 10 centimeter. So this linearity is can be achieved, okay, properly because of the term here. Okay, the term here, whereas R32, okay, is only at the numerator and RA is fixed. So only R32 change, okay, will affect the V out. as compared to the voltage divider circuit, where due to the change of the formula, you can see proof by the formula, the change of the potentiometer may not be proportional to the displacement. So this is how we can achieve we can maintain the linearity of the resistance versus the output, which is the displacement. Okay. So there's other way where you can other method that we can use as a signal conditioning uh, for the potentiometric or resistive device. Okay, by using a Western bridge. Okay, Western bridge basically is one method where you uh, connect your sensor into like what is shown in this picture. So when the bridge is balanced, okay, basically V out will be equivalent to zero. Okay, so this is uh, one example. I don't want to go through in details. Maybe you have go through it before. Uh, so the concept of Wilson bridge, where we can be used or signal with resistive device, like for example, uh, strain gauge, thermocouple. Okay, whereas the resistive change due to the parameter, you can convert into voltage output. Okay, and then we have other device. Okay, like inductive device. Okay, where the inductance depends on the number of turns. Okay, like remember our relay. But our relay basically um, device depend on the magnetism of solenoid and so it actually depends on the reluctance created by the magnetic field. Okay, so there are many derivation device based on the inductive measurement. Another device is called as capacitive sensor. Capacitive sensor, okay, basically the capacitance we use to measure the parameter change. Okay, so we know that the the equation of capacitance of two plates. Okay, okay, one and two. So the capacitance, okay, basically proportional to the relative dielectric constant, okay, between the plate, o- and also proportional to the effective cross section area between the two plates, and inversely proportional to the distance between the plate. Okay. Uh, okay. So this basically device. Okay. There are a few ways. Okay, how we can use to measure parameter or physical inputs for example distance. Okay, we can okay configure it to detect the change of distance. Okay, okay, or we can configure it to detect the change of relative permittivity or the change of area between the parallel plates. Okay, so there are a few ways how we can use, okay, the device. So for example, okay, this is a capacitive displacement sensor designed to monitor small change in workpiece position. There are two cylinders. Okay, two cylinders. There are two part of the cylinders. First part is the top part, and second one is the bottom part. Uh, so basically, the top part is inserted into the bottom part. So the bottom part cylinder size is slightly smaller than the top part. Okay. So and then there is a distance between the uh, top part with the bottom part. Okay. So the inner surface area is in between the top part and the bottom part. Okay, will uh, change or vary when there is a displacement. Okay, so in this case, it's the two metal cylinders. Okay, the cylinder are separated by plastic sheath or bearing. So that will make sure there is no direct friction between the two cylinder. Okay, so the two cylinder is constantly distant. Okay, uh, uh, and then the distance is 1 millimeter. Uh, and the direct constant at 1 kilohertz of 2.5. The direct constant is basically 2.5. And why there's 1 kilohertz? Because this is uh, capacitor can work at AC level. Okay, so denote that the frequency it work at AC level lah, AC signal. Okay, so if the radius, okay, basically the radius, okay, of the top part is 2.5 centimeter, find the sensitivity, okay, in picofarad per meter as the upper cylinder slide in and slide out of the lower. Okay, so there are two questions. Number one is sensitivity, and second one range. Okay, what is range? So to solve this, we are a bit ahead of our whereas in our next topic I will explain about sensitivity. But anyway, I will explain it now. So sensitivity, okay, for a device, okay, device. So it has its input and then the output. So sensitivity by definition is the change of output divided by the change of input. Okay, that's sensitivity. Okay, so if we plot, okay, the output versus input, assuming the response is linear, assuming. So sensitivity is basically the slope. Okay, delta output over delta input. So sensitivity is the change of output divided by the change of input. Okay, so that is sensitivity of a device. So in this case, it has given the sensitivity is in the unit. Okay, picofarad per meter. Picofarad per meter. Okay, so the term change. Okay, okay, delta. Okay, okay, can so basically D there we can in this case. Okay, C farad capacitance, M is the one of the parameter. Okay, okay. So in this case, we want to find the sensitivity. What the input is basically uh, the displacement. Okay, then the displacement basically change the height. Okay, the height h in this case h. Okay, so sensitivity in this we might need to find the derivative dc or the effective capacitance to the height. Okay, we need to find that. Okay, oh I mean sorry. Okay, but before that we need to find the equation of uh, the equation of the capacitor in this design. So uh, it has a okay cylinder area, okay, which has a radius r. The r radius, okay, and height h. Okay, so we know that c capacitance is epsilon 0, epsilon r, a over d. Or the distance. Distance d is distance between the plate. So in this case, distance okay, is d. Okay, distance. So that's fine. So we need to find the effective area. The effective area. Okay, the effective area. Okay. So the effective area A is given as 2 pi okay, r the radius okay, multiply with the h. Okay, so you need to find this. That's the effective area. Okay, or circumference lah. Okay, so that's the effective area between the two plates. Okay, 2 pi r is uh, the circumference. Okay, and multiply with the h. So that's the effective area between the plates. Okay, so if we insert that, we get that 2 pi k epsilon naught r h over d. K is the yeah. This is k. K the dielectric constant k. Okay, that's the dielectric constant. Okay, now we get here. So can so remember that I mentioned, okay, sensitivity is the change of output divided by change of input. So here is the sensitivity unit has been given, picofarad over m. M is the unit of the parameter. So we know that this is the displacement. So displacement, uh, when there's a displacement, so we change the h parameter. So that's why the sensitivity can be calculated or can be estimated using this, okay, estimation, this the derivative of capacitor, total capacitance, effective capacitance over the change, okay, the change of capacitance over the change of height, or okay, the parameter of h. Okay, so we so if we derive dc over dh, we get that 2 pi k epsilon 0 r over d. Okay, okay, and then we insert all the value. Remember that we calculate that in meter. Okay, so that finally we get 3, 4, 7, 5 picofarad per meter. So that's the sensitivity. Okay. Okay, so the second part, what is the range? Okay, if vary from 1 centimeter to 2 centimeter. Okay, so I think you can find, okay, the answer, the range, okay, using this. Okay, okay, the answer. So I give you, okay, 10 minutes. You can try to figure out what's the range, the minimum capacitance, and then the maximum capacitance. Okay, H is already given 1 centimeter to 2 centimeter. So try to find. I think give you 10 minutes to calculate, and then we will show our answer together. Let's see whether
Doctor.
So okay, so like I said, you have the capacitance as the output, okay, H as a variable of all the displacement, basically the input, okay. Uh, so if C 0, okay, so will be the slope, okay, basically is the sensitivity, okay. So it's like a linear equation C equal to M H. Okay, so you just you gonna just apply basically this is sensitivity. just plug in or insert the value of the edge. Okay, 1 centimeter, so you get this the minimum. Okay, minimum at 1 centimeter. Okay, and the maximum is at 69.50 picofarad. So that's the answer that I get. Okay, so that's